Hi students, it's Dr. Marks. I've created this presentation so we can have some more practice with hypothesis testing. It's very important that you understand this topic very well before we move on to some of our other topics that we're going to cover in this class. What I've done here is created a series of questions that I think will help you both with quizzes and with projects. So question number 1, you think that mean test scores on an English test will be higher for native English speakers than for English as a second language speakers. So this is your hypothesis. You're given a test in English to people that are English native speakers and non-native speakers of English. All right, so my question is, what kind of hypothesis are you creating? What kind of hypothesis test are you creating? Is this going to be one-tailed or two-tailed? Now let's very quickly review this. When do you use a one-tailed test? Well, when you think there's going to be a direction, you think this mean is going to be higher than that mean. If you don't have any expectation and it's purely exploratory, I just want to see if the means are different or if they're the same, but I don't have any expectation for which is higher, then it's a two-tailed test. So in this case, you're given an English test, you think that people who speak English as their primary language are going to have higher test scores. Everyone agree this is going to be a one-tailed test. So it's important that you understand when you would use a one-tailed test and when you would use a two-tailed test. If you think it's a one-tailed test, you need to have some logic behind it. So as you're going to see, one test is a little bit easier to pass in terms of clearing the bar, right, clearing the hurdle, than the other. And so if you're going to do a one-tailed test, you need to be able to justify it. Second question, and it's the same question I just asked you. Based on this English test that you're going to be given, how would you write out this hypothesis? So I'm asking you specifically about the hypothesis that says that test scores are going to be higher for those who speak English as a primary language versus those who are English as a second language. So this is what would become your alternate hypothesis. So let's think about how we would write that. Well, does everyone agree? It would be that the mean for native speakers has to be greater than the mean for ESL speakers, right? And as I said, that's going to be your alternate hypothesis if you're doing a one-tailed test. So the thing that you think is true goes in your alternate hypothesis, all right? And it's kind of strange language. Why the alternate hypothesis? I don't know why we call it that. Now, another thing I want you to realize is that there's more than one way to write this hypothesis, right? So I could say mean 1 is greater than mean 2, or couldn't I also say that if I take the mean for native speakers minus the mean for ESL speakers, that one minus the other is going to be greater than 0. Because I think the mean for native speakers of English is going to be higher. So these are equivalent statements, and it's possible that I could change it up a little bit on quizzes. So it's important that you are able to understand that these are the same. All right, so far so good. That's pretty easy stuff. All right, same question about our English test. Now I want to know, what is the null hypothesis when you're crafting your hypothesis test? So what is the null hypothesis? Remember, we've just said that that directional assumption, that one mean is higher than the other with a one-tailed test, that goes in your alternate hypothesis. So remember, the null is the thing that generally with a one-tailed test, we're hoping to reject. So if we think one mean is greater than the other, then usually we would write in the other hypothesis that the means are the same. Now, technically, if I think one mean is higher than the other, I could put that the opposite is true in the null hypothesis. But again, when we get to regression, that's not going to be as clean. So if you wrote it this way, this would be fine. The mean for native speakers is equal to the mean for our ESL learners. So that's the null hypothesis. And remember, that when we have a one-tailed test, we're hoping to reject this null hypothesis, right? Now, is there another way to write this hypothesis? Yes, there is. Do you agree that we could just rewrite this as our null hypothesis being that the mean for native speakers minus the mean for ESL speakers, if they're equal, when I take one minus the other, it has to be equal to 0. So look at those for a second, and do you agree that those are equivalent statements? All right, so question number 3. We've just decided it's a one-tailed test. We know how to craft our alternate hypothesis. That's where the directional assumption goes. And then the null hypothesis, the thing that with a one-tailed test we are trying to reject. All right, question 4. Let's move on to something else. You are comparing salaries for female and male CPAs with similar degrees and years of experience. All right, so I'm trying to hold all else constant as much as possible. Males versus females, maybe they all have master's degrees and all have between 8 to 10 years of experience. You have no reason to believe that the means will differ. You're just simply trying to explore this. You're trying to see if there is some kind of discrimination. This is not going to be a very robust test of discrimination, so let me be very clear about that. What kind of hypothesis test are you running? So in this case, would this be a one-tailed or a two-tailed test? One-tailed or two-tailed test? Hopefully you said two-tailed test. Again, a two-tailed test is when I don't have an assumption of direction. I don't think that one mean is greater than the other. I don't have any reason to believe females are greater than males or males are greater than females. So maybe this is exploratory, or if they're different, I don't know which one's going to be greater. So if that's your belief, then you'd be running a two-tailed test. All right, so same question. You're comparing the salaries for female and male CPAs, holding constant the degrees they have in their years of experience. You don't think the means are going to be different, or if they are different, you don't know which is going to be higher. But now we want to write out the null and alternate hypothesis that you will use. All right, so take a second and see if you can craft the null hypothesis and the alternate hypothesis under the assumption, right, of a two-tailed test. So take a second and see if you can craft that really quickly. All right, so hopefully you know it's a two-tailed test, right? You've got a null hypothesis that says means are equal. Means are equal. And your alternate hypothesis is simply that the means are not equal, right? I can't say that I think males have a higher mean than females or vice versa, but I'm simply trying to explore if this is true. Now, a lot of times in these lectures, I say that we want to reject the null. That's normally because the kind of work I do, we're doing regression, and that's usually the case. But if we were really doing this and we were hoping that we don't have any kind of gender discrimination, wouldn't we be kind of wanting to fail to reject the null? Well, you would. But again, this is not how you would do a discrimination type of analysis, because we're not holding things constant that could matter. We're going to talk later about how would we do this in a more robust way. But this is our two-tailed test. Either means are equal or they're not equal. And the thing that has the direction or the unequal always goes in the alternate hypothesis. All right, so now we've got our two-tailed test. Now, same example with our CPAs. And let's say that we want to be 95% confident in our result. And hopefully you understand what that means. Remember, we've also talked about that when we're doing work like this, inferential statistics, usually 95% is considered to be kind of a robust result. Sometimes you might see things discussed at 90%, but you would have to admit that that's a pretty weak result. So you really want kind of as a lower bar, lower threshold, 95%. Hopefully things are more robust than that, but 95% generally we would say, okay, this seems like a solid result. All right, so we want to be 95% confident in our results. So my question here is, what is your alpha level? Because alpha is important when we're looking up our t-statistics from our critical t-tables, right? So what is our alpha level? Well, everyone agree, if I want to be 95% confident, then our alpha is equal to 0.05. Now there's some confusion about alpha. Alpha is driven by our confidence level. It's not driven by whether we have a one or two-tailed test. And I'm going to talk about that in just a minute. But alpha comes directly from your confidence level. So what does it mean then when we say we want to be 95% confident or we have an alpha of 0.05? Well, what does this mean? It means that the probability of rejecting the null when it's actually true is no more than 5%. So let's read that again. Our alpha of 0.05 means that I want to have only a 5% chance or a 5% probability of rejecting the null when it's actually true. So in other words, we'd be making an error, right? If we're rejecting the null when it's actually true, then we've made an error. So we're saying we want to limit that error to 5%. So we're saying this is what I'm willing to accept in terms of the probability of making an error in our conclusion. Now, as I said, 95% confidence would be a pretty robust result in the kinds of work I do. But maybe if you're in the medical field and you're talking about efficacy of a medicine or something like that, maybe 95% would not be acceptable in terms of a level of confidence because you're dealing with people's lives. I'm just doing things like analyzing student test scores. So you understand, but it would be a pretty robust result. All right, question 7. We're still talking about these salaries for male and female CPAs. We've just said we want to be 95% confident in our results. So the third bullet says, which graph depicts the correct illustration? Which graph is the correct illustration? So go back and read that scenario one more time, and then tell me which graph would be the one that matches our scenario. All right, now remember, the key thing is we said in the first bullet, you have no reason to believe that these means will differ, or if they do differ, you don't know which would be higher. So what did we say? We're running a two-tailed test. If we're running a two-tailed test, then we're setting up a set of hypotheses that is going to work like what we see on the left. What's the difference? On the right, it'd be for a one-tailed test. On the left, it's for a two-tailed test. Notice for the two-tailed test, you have your rejection region that is divided into both tails. These graphs are never really as accurate looking as I want them to be, because one thing that you need to understand, and this is important, add together the alphas. Whether it's the graph on the left or the graph on the right, they're both 0.05, right? Because it's not one or two-tailed test that drives our alpha, it's our 95% confidence level. So with our 95% confidence level, we have an alpha of 0.05. The graph on the left simply says, look, when you're running a two-tailed test, some of your rejection region is going to be on the left and some's going to be on the right. The graph on the right says, look, when you're running a one-tailed test, then all of your rejection regions got to be in one tail or the other. All right? But notice they have the same alpha. So that seems to cause some confusion. Alpha does not depend on whether it's one or two-tailed. How we divide it up graphically matters, but it's still 5%. All right. Question 8. We're still comparing these salaries for female and male CPAs. Again, we know that we're running a two-tailed test, and we want to know, what if we wanted to be 99% confident in the results? So think about what we're doing there. What happens to alpha? What happens to the graph? So we want to be 99% confident instead of 95% confident. So what we're saying here is we're willing to accept only a 1% chance of error. Before we were willing to accept a 5% chance of error of rejecting the null when it's actually true. But now I want to be more confident. So I want to reduce that chance of error. Well, that means then we're going to require more precision than before. If you think about it, when our alpha is now 0.01, those tails change. So look at that picture for just a second with our distribution, and you see those red regions? Well, if you require more precision, then that rejection range has to get smaller, right? There's a less chance. You have to have a higher bar, in other words, to be able to reject the null. And so fewer opportunities to reject the null. So when you do reject the null hypothesis, you can be more confident that it's actually true. So this rejection region is going to shrink. Those red portions of the graph are going to get smaller. Now, if we have a two-tailed test, which we do, remember that alpha gets divided in half for each tail. It's still a total of 0.01. Alpha hasn't changed, right? 99% confidence means 1% chance of error. Alpha is 0.01, but half of it goes in the upper tail and half goes in the lower tail. So it's 0.005 in each tail, but it still adds together to be 0.01. So bottom line, what we're saying here is with 99% confidence, we want to be more precise. We are going to raise the bar. So in our hurdle example, we're basically raising the hurdle. You're going to have to work harder to get over the hurdle. If you get over the hurdle, it means you've got more evidence that we can reject the null hypothesis. All right, question number 9. Does a one-tailed versus a two-tailed test impact our alpha level? Hopefully we can answer that now. And what drives the alpha? And what does a one versus two-tailed test impact? What does that distinction matter with respect to? So I have a few questions going on here. So let's go back again to our picture, and we remember that I've got 0.05 alpha here for both pictures. One's one-tailed, one's two-tailed, right? Right is one-tailed, left is two-tailed. But the alpha still adds to 0.05 because alpha has nothing to do with if it's one or two-tailed. Alpha has to do with what? That level of confidence. Do you want to be 95% confident? Do you want to be 99% confident? Sometimes I do studies where I can report 99.9% level of confidence. Okay? But alpha has nothing to do with one-tailed or two-tailed. So we understand that. So we want to know, the third bullet says, what does one versus two-tailed impact? Well, that's a really good question. And so I'm going to have to kind of back into it by illustrating for you why one-tailed versus two-tailed matters. Why can't you just say, eeny, meeny, miny, mo? Why does it matter? Now, we're going to come back to that in just a second, because before that, we need to answer question 10. How do we determine degrees of freedom? And how does it influence our hypothesis test? So, degrees of freedom, it's a pretty abstract concept that is hard to really understand, but we need it because it helps us know what our critical T is. So first we have to calculate degrees of freedom. Degrees of freedom is n minus 1 for the first group and n minus 1 for the second group. So if I'm comparing mean for females and mean for males, maybe N1 is number of observations for females, N2 is number of observations for males. So N1 minus 1 plus N2 minus 1. Now, why do we need degrees of freedom? Because it impacts the hurdle that we're going to need to clear. So back to that hurdle example, that hurdle, how high that hurdle is a function of our degrees of freedom. So I'm going to illustrate that to you. In other words, how much evidence must we have against the null hypothesis in order to be able to say we can reject the null? So as the hurdle gets bigger, we have to have more evidence to be able to reject the null hypothesis. Now, how do you determine the degrees of freedom and how does it influence the hypothesis test? Well, that requires us to take a look at this critical T. Now remember, the critical T comes from our table. let's assume, just for illustration purposes, that we have a one-tailed test. And let's say that we want to be 95% confident, just in whatever test we're running. We're going to run a one-tailed test, doesn't matter what it is. We want to be 95% confident. So we know that our alpha is 0.05, and in this case, it's all going to be in one of the tails. Now, if degrees of freedom is 25, then we can go to this table and find our critical T. So let's do that. But before we do that, make sure you understand our critical T is the hurdle, right? It's the hurdle that we have to get over. And I'll cover that again in a second. So look at this table for a second. When degrees of freedom are 25, right? And that's tied to the number of observations we have. And we want to be 95% confident where alpha is in just one tail, 0.05 in one tail. Let's find that. So does everyone agree? Since, take a look at this table. It shows you a picture. It is measuring it for the right tail. And it says T distribution area in the right tail. So since this is a one-tailed test, then I need to find 0.05. Now follow that down to degrees of freedom of 25, and we get 1.708. So that's what we're saying. We have to clear that hurdle if we want to be 95% confident with 25 degrees of freedom. But what if degrees of freedom is only 15? Take a look at that table, right? I'm not changing alpha. Does everyone agree that we get a critical T of 1.753? Okay, so what has happened here, guys? What conclusion can we make? We kept everything the same, but we changed the degrees of freedom. And that degrees of freedom comes from our numbers of observations. So think about what we just learned. When you have fewer observations and therefore fewer degrees of freedom, what happened to that critical T? It got bigger. In other words, fewer observations means that bar, that hurdle, the height of the hurdle you have to get over, it's gone up a little bit, right? So now, when your degrees of freedom are only 15, you have to have just a little bit more evidence against your null hypothesis to be able to reject it. So how high that bar is set that you have to clear is a function of degrees of freedom, which is a function of the size of your observations, the number of observations. All right, you seeing this? So that's why we don't have just one row. We have to have different rows on our table here for the different numbers of possible degrees of freedom. Now, what if I was running a two-tailed test? So, question 11, two-tailed test. We just talked about this for a one-tailed test. Let's stay with 95% confidence, so let's stick with alpha of 0.05. Now, remember here, this table reports area in the right tail. So it's set up for a one-tailed test. But if you fully understand this idea of alpha, we can still use this, right? Because with a two-tailed test, what do we know? We need to look at half of the alpha in the upper tail. It's still a total alpha of 0.05, but only half of that is in the upper tail. So half of it in the upper tail means that only 0.025 is going to be in the right tail, which means now I need to look at the green column. Instead of 0.05, I'm looking at 0.025. Now, let me stop you right there because I want to be very clear. I have not changed alpha, right? We are still 95% confident in terms of that's the level we want. I haven't changed that. Our alpha is still 0.05. All I'm doing is moving some of that alpha to the other tail. It's just in terms of how I'm reading this T distribution. So don't tell me, oh, but you said alpha would change. I did not say alpha changes. Be very clear about that. So let's take a look. If our degrees of freedom are 25, then our critical T is 2.060. Right? Take a second, make sure you agree with me. Very bottom of that green column. If our degrees of freedom are 15, Then our critical T, take a look. You tell me what it is. See if you find it. 2.131, am I right? Yes, all right. So we have the same result. We just said, look, degrees of freedom is related to numbers of observations. When we have fewer degrees of freedom, because our number of observations have shrunk, then the bar we have to clear has gone up, right? It's gone up from 2.060 to 2.131. Well, that makes sense. If you have less data, if you want to be 95% confident, you've got to clear a higher bar, right? We have to have more evidence against the null hypothesis because we don't have as much data. But let's compare to what we had before. So when we had a one-tailed test, look at what our critical T was. For 25 degrees of freedom, it was 1.708. Now it's 2.060. It went up. And before, when we had a one-tailed test at 15 degrees of freedom, it was 1.753. Now it's 2.131. All right, so what can we just say? What happened to the hurdle that we have to clear, the amount of evidence we have to have, when we changed from a one-tailed to a two-tailed test? So the two-tailed test has a higher bar, right? The critical T, those cutoffs for determining if we have enough evidence to reject the null, they actually went up, right? So what does that tell us? The bar got higher. So before I get to this last bullet, then what does that mean? Which is, if I was going to ask the question, it's kind of an awkward question, but if I was going to ask you, which is harder to pass, a one-tailed test or a two-tailed test? In other words, when is it harder to reject the null? And when is it easier to reject the null? Well, do you agree with the two-tailed test? It was harder to reject the null. So if you do a one-tailed test, it's going to be a little bit easier test to pass in terms of rejecting the null. So you better have a good reason for running the one-tailed test because it's got a lower bar. So for this reason, as the last bullet said, some research might always just run a two-tailed test because it's a more rigorous test. But for our purposes, again, as we just said, two-tailed, it's harder to reject the null, but we're still going to use one-tailed and two-tailed because I want you to understand it. Because when you're reading other people's research, they may talk about two-tailed and one-tailed, or they may just do everything as a two-tailed. And that would be okay because that's going to be a slightly more challenging test when you're trying to reject the null. All right, hoping that makes a lot of sense to you. All right, question 12. What is the decision rule for a t-test? So again, when I say t-test, this is really the decision rule for a t-test, but we're using the t-test for our hypothesis testing, our comparison of means. You will be using t-tests for other things as well. We're going to use it in regression analysis. If you've already had some regression analysis, you remember using the t-test. If you know how to do it in this context, you're going to know how to do it in any context. So what is our rule? Now remember, going back to our hurdle and hurdler analogy, we have a hurdle right there in red. And that's the threshold of required evidence that we have to have for our given confidence level. Remember, we want to be 95% confidence. Well, then this is our threshold. But if we want to be 99% confident, then that threshold goes up a little bit. And that comes from our T distribution, right? That table that we were just looking at. And we call it the critical T or the T critical. I kind of go back and forth in my language here, so I apologize, but critical T. Then we have the hurdler, and that's our statistical result. That comes from our data. So Excel is going to calculate stuff and give that to us, and it's going to give us a T statistic. So when you're doing your test, you're trying to find out, is my T statistic that comes from my data large enough to clear the hurdle that's created by this critical T that comes from the table? Put another way, as we just said, T statistic comes from our Excel output, positive or negative. I'm going to show you. It could be either one. So if you get negative numbers, don't stress. That's fine. I'm going to show you why that happens. We're going to take the absolute value. Then we have our T critical, that comes from the table. And note that it's always expressed in the positive, even though you could have area in the left tail, right? But it's always expressed in the positive. So this now allows me to compare apples to apples, absolute value of the T statistic, compare it to our critical T. And this is our final rule. We reject the null if the absolute value of our T statistic is greater than our T critical. Now, if you don't take the absolute value, you're going to have a problem because it wouldn't be fair to say, oh, it's negative, so it's less than the T critical. That makes no sense. We have to compare apples to apples. If our T critical table is always expressed as positive, then we have to look at the absolute value of the T statistic. So this is going to be very important. The absolute value of the T statistic, is it greater than the T critical? Now, later we're going to discuss what happens if your sign is wrong because you thought this mean would be bigger than that mean, but it's actually the other way around. I'm not going to worry about that for right now. All right, question number 13. Can a T statistic be negative? Well, I kind of just answered that question, but I also want to go over this again and let you take a look. So the answer is yeah, sure it can. Let's look at this output right here. This is a 2-sample t-test with equal variances that somebody ran. And if we look at their t-statistic, they get a t-statistic of negative 3.7341. All right. They also carry a whole lot of digits. By the way, I'm not going to care if you carry this many digits in your table. I usually round to 2 behind the decimal. Unless it's 0.00 something, then I would probably need more digits, but we don't need to have quite this many digits in our projects. So we have a negative t value here. So the next question asks, why is a t statistic negative? Why is a t statistic, oh, bad grammar there, but you know what I mean. Why is a t statistic negative? Well, let's take a look. Let's look at that numerator. What are we doing right there? We're taking one mean minus another mean. Well, what happens if mean x2 is larger? If x2 is the larger mean and x1 is the smaller mean, isn't that numerator going to be negative? Well, this is all we're doing when we calculate that t statistic, but Excel's doing it for us. So we're taking the difference in means, and depending on which one is mean number 1 and which one is mean number 2, it could be positive or it could be negative. Now, the denominator is going to be positive, but the numerator could be positive or negative, and that's where that negative sign comes from. But guys, this is the calculation that's going on behind the scenes when we have our statistical software do this for us. But it also means that we can calculate this by hand if we wanted to. And you're going to find a lot of examples online of people calculating this by hand for AP tests for high school students, that kind of thing. Well, we need to understand it, but once we understand it, we don't want to calculate this by hand. That would be a pain. So this is what Excel is doing for us in the background when it spits out our t statistic. So it clearly can be negative. All right, so we've just answered the question, can a t statistic be negative? Yes. And remember, that's why we have to take the absolute value when we do our hypothesis test. Because the critical t in the tables, they're always expressed as a positive. And we're going to work with them again in a minute, and you're going to see that they're always positive numbers. So it wouldn't be fair for me to take a negative t statistic simply because of which group was assigned group 1 and which group was assigned group 2, and compare it to a critical t, which is my hurdle we have to clear, unless I look at the absolute value, right? All right, so remember, we reject the null if the absolute value of the t statistic, meaning let's get rid of the negative there, is greater than the t critical. All right. Question 14 says, all right, t-tables sometimes look different. Does it matter which I use if it's expressed as a one-tailed or a two-tailed table? In other words, do I have to use a one-tailed t-table when I do a one-tailed test and a two-tailed table when I do a two-tailed test? And the answer is no. If you understand alpha, you can use whatever table you want. You just have to manipulate things a little bit. You'll probably see that on quizzes that I use different tables because I expect you to understand this idea of alpha. And once you understand the alpha and how it works and what it means graphically in terms of one versus two-tailed tests, you can manipulate the information in the table. So let's take a look and see if we get the same answer. The answer is going to be we will, but I want you to see this for yourself because you need to be able to manipulate things in this way. Now, let's stick with degrees of freedom of 25 and 95% confidence. Let's do a two-tailed test and see if we can find our critical T, remember that hurdle that we have to get over in order to reject the null hypothesis. So here is our two different T tables. Now, take a look at these because it's important that you understand when I give you a T table or you use one, you need to make sure you know what you're working with. On the left, it's clearly designed as a one-tailed test, right? Because look at the picture. It has all the area for alpha in the right tail. And then it also says T distribution area in the right tail. But let's use the table on the left. And we need to remember that if we're doing a two-tailed test, 95% confident, then we have 0.025 in the upper tail and 0.025 in the lower tail. Well, since this table is only capturing the upper tail, then I have to look in the column and I get at 25 degrees of freedom 2.060. Remember, I didn't change alpha. I just have to remember 0.05 has to be divided into two tails, but the table is just reflecting the upper tail. So the upper tail has to change to 0.025. All right, let's look at the table on the right. The table on the right is designed for two-tailed tests. Well, with two-tailed tests, all I have to do is look at my 0.05 because it's already kind of added it together for me, the two tails, go down to 25 degrees of freedom, and I get 2.060. Do you see that these are the same answer? Why? Because it's a standard T distribution. It doesn't change. You just have to learn how to read the tables. So make sure you understand that on the right, it's a two-tailed T distribution table. It's already saying, look, if we're doing a two-tailed test and you have a 95% confidence level in alpha of 0.05, this is what you do. On the left, it's saying, we're going to design this for one-tailed test. Hey, if you want to do a two-tailed test, don't forget, half your alpha has moved to the lower tail, but this table reads only the upper tail. The upper tail, instead of being 0.05, is 0.025. All right, enough said. Hopefully you followed that, and that makes total sense. All right, so let's move on to question 15. And now we're going to look at some data. So here we have mean sales for two different marketing methods, A and B. And you see in the right, we have two columns of data, and this is Excel output, method A and method B. Now, we want to test, as the second bullet explains, if mean sales are different. Are mean sales different? Let's assume, as the third bullet says, that there's no expectations a priori. I don't know if A is going to be greater than B or B greater than A. So I'm going in with the expectation that I'm going to run a two-tailed test. Now, two-tailed is the more robust test, right, in terms of you have to be able to clear a higher bar to be able to reject the null. So, I mean, that's fine. Clearly, I can look at my mean and I can see that we got some pretty different levels of sales. However this is measured, it could be in hundreds, thousands, number of units. It doesn't really matter. But we see the means are pretty different. So it's kind of a duh example in that clearly there's going to be some statistical difference here. We can clearly see that there's going to be a statistical difference with a mean of 7.1 for method A and or 71 rather, 0.5 for method A and 84.7 for method B. But at what level of confidence can we say this? 95%, 99%, maybe even 99.9%? Well, I need to determine that. But also remember, if these means were closer, maybe it's 71.5 and 72.2. All right, now they're close. And I don't know if that's statistically significantly different, or maybe it's just due to chance. So I tried to find an example where they were really close together, but I did not find a good one. So I'm basically trying to say, look, Are these really different in a statistical sense, or is this difference simply due to chance? All right. So here's the data I just showed you on the previous table. This would be your Excel output. And just so you know, not all statistical packages give you all this stuff. So this is what Excel looks like. And we said we're going to do a two-tailed test. And so on the bottom of this in red, I am showing you that you get the p-value for a two-tailed test and the critical t for a two-tailed test. Now, here, it's really rich in terms of giving you everything you need. So keep that in mind, that there's no excuse to not get this right, because Excel basically gives it all to you. You don't really have to even think. It also gives you your degrees of freedom. Remember, how do we get the degrees of freedom? We take the observations. We have 15 observations for method A and 15 for method B. So 15 minus 1 is 14, plus 15 minus 1 is 14. That's where they got the 28. And we have a t statistic of negative 4.083. Why is it negative? Because we used method A, the mean for A minus the mean for B. If we switched it and we made it opposite, if we called A B and B A, then it would be positive. So that negative sign's nothing to worry about, but remember, we do have to take the absolute value. Okay, so we have everything we need to do our hypothesis tests. Now, you might be wondering, if you were going to do a report with this kind of information, could you get rid of some of this stuff? Yeah, you could. Now, what might I consider getting rid of? I'm doing a two-tailed test, so I'm not sure I really need that one-tailed information. And I've got the variance. I'm not sure I need the pooled variance, and the hypothesized mean difference of 0 basically is just saying I am hypothesizing that there's either a difference between or there's not a difference. I'm not saying I think they're going to differ by 10, for example. All right. So we can clean up this stuff, but how do you know what you can get rid of and what you can't get rid of? Well, my note to you is that you should keep what you need to replicate these results. And if I know the mean and the variance and the observations, we can do this by hand, right? Now, degrees of freedom I'd keep 2 just because it saves a step. But if I have degrees of freedom and our t-statistic, I can go to the table and do this myself as well. So keep those things that somebody would need to make sure that your results are correct. All right. So let's go back to our hypothesis test. Remember, we're doing a two-tailed test. So our null hypothesis is that the means are equal. Now, I didn't put all the symbols in there, but if I was writing this up in a report, I might write this a little bit more sophisticatedly. So we want to know, can we reject the null hypothesis? Remember, we're asking, do we have enough information, enough evidence against the null hypothesis to be able to reject it? So we have to use our rule. I need to compare the t statistic to the critical t, but I actually need to do an absolute value of the t statistic. So I kind of sometimes forget to write that because for me it's just innate and ingrained, but you need to remember it's always the absolute value of the t statistic. All right, so we're asking, can the hurdler, which is the t statistic, get over the hurdle? Is there enough evidence as determined in that t statistic to clear that t critical? Well, our t statistic is negative 4.083, but we take the absolute value and we have to get the t critical from either the table, like the t distribution table we've been working with, or our output. Now, I don't normally get this t critical sitting there, so you've got it sitting there right in front of you, but we can also look it up on the table. Remember your degrees of freedom. We know where that came from. It was 15 minus 1 plus 15 minus 1 gave us 28. It is here on the table, but maybe in a quiz question, you would need to be able to calculate that. So I'm just reminding you of that. Let's say that we're going to test at the 95% level of confidence, and that's what was done here. Remember, when you're doing this in Excel, you're going to have to tell it what level of confidence you want. So if you want 95% confidence, you got to tell it that. If you want to test it 99, then you need to tell it that because your alpha is going to change. All right. Now, let me just remind you that we can go to this table. We can look at, this is a two-tailed t distribution table. So we've got 0.05, 28 degrees of freedom. Our critical T is 2.048, but that's also what the Excel output told us, right? So I'm not saying you need to confirm because obviously it's going to be right, but I'm showing you that that's where it came from, all right? So take a look right there at the very bottom row. The T critical for a two-tailed test is 2.048, and that is what we just found in the table, all right? So that's where that's coming from. So we've got our null hypothesis. The means are equal. We want to know, can we reject the null hypothesis? Is the T statistic, or the absolute value of the T statistic, greater than the critical T? Is the hurdler greater than the hurdle? All right, so we've got our T statistic of negative 4.083 and our T critical, which we've just found two ways. It's on the table of the output Excel gave us, 2.048. We also just found it in our table for our T distribution. And we see that the absolute value of the T statistic is indeed greater than the T critical. So what does that tell us? We can reject the null hypothesis. In other words, there is enough evidence that we can reject the null hypothesis, which said the means are equal. Well, that's not a very surprising result, right? Because if you look back at this data, our means are pretty dissimilar, 71.5 to 84.7. I would have been shocked if we couldn't reject the null, right? If we had failed to reject the null. So remember, our options are reject the null or fail to reject the null. All right, so you get the idea here. Now, I know some of you also understand that there's another way to do this, and that's to look at p-values. I warn you though, for you to work with p-values, you better understand p-values. If all you do is memorize cutoffs, that is not really showing a mastery of statistics, so make sure you understand this. Now remember what the p-value is. The p-value captures the probability of rejecting the null hypothesis when it's actually true. So read that again. The p-value is the probability of rejecting the null hypothesis when it's actually true. In other words, we reject the null hypothesis that the means are equal. So we're saying, hey, the means aren't equal, rejecting the null hypothesis. But it turns out that it's actually true, that the means are actually equal. So we don't want to have much probability of this, right? This is making an error. So p-value is the probability of making an error. And that error is rejecting the null hypothesis when it turns out to be true. So we want to have a very small chance of making this error. Now, as you see in the right, we have a p-value of 0.000336. It's a very small number, right? Very, very small number. So what that means is that given the evidence from this data, there is a very tiny chance of making an error. It's highly, highly unlikely, right, that we are going to reject the null hypothesis in favor of the alternate hypothesis when it turns out that the null hypothesis is actually the correct one, right? Really tiny chance. So obviously we have very strong evidence against the null hypothesis, and that's why we have that pretty big t statistic, negative 4.08. Now, if you do a whole lot of statistics, you're going to get to the point where you can look at something like that and go, oh yeah, that's going to be highly significant. I mean, I could look at that and I know exactly how significant that would be, even if I didn't have the critical T and the p-value there. You just kind of get used to knowing. So that's a pretty big t statistic. All right, so we would reject the null hypothesis. Now, given the p-value of 0.000336, do you agree that really we could say that we can be more than 99% confident, right? If we're 99% confident, then we would have a p-value of 0.01. Well, this is far smaller than 0.01, right? So this is even stronger than saying it's significant difference in means at the 99% level of confidence. We could say something even stronger than that. Now, if you're using the T statistic versus the critical T approach, like that's how you do it, and there'd be nothing wrong with doing it that way. In fact, when I was in graduate school in the olden days, we didn't even have these things called p-values, so it was always this kind of way. So if you're doing it that way, let's say you do a test and you find, hey, this is significant at the 95% level. Well, is that where you stop? No. You should probably then see if it's possible that your result is significant at the 99% level. We see that this is a statistically significant difference in means, right? We just went through that whole analysis to say that mean A is different than mean B. They are statistically different. But can we say it at the 99% level of confidence? Well, we know from the p-value we can. But you should take a minute and go back to one of those T tables and just confirm that I'm right. How would you do that? You know you have a T statistic of negative 4.08. Take that absolute value and compare it to the critical T from your table. But now your critical T has to be for 99% confidence level, an alpha of 0.01. Well, you're going to see that I'm right. But you should be able to go do that yourself and convince yourself that even if you didn't have this p-value, that you could determine that this is a statistically significant difference in means at the 99% level of confidence. All right, let's move on to question 16. Here you have scores from some health screening that's taken by males and by females. And we want to see if there's a difference in means. But again, we have no reason to believe one would be higher than the other. And if they are different, we don't have any reason to think that it'd be males or females. So this is more exploratory. So we know we want to have a two-tailed test. Let's assume we want to be 95% confident in the conclusion. All right. So we have test scores for males and females for this health screening. We're going to run a two-tailed test at the 95% level of confidence. Now, here you see that this was set up to be a two-tailed test. So this is not Excel output, but it doesn't matter because we still know how to read it, right? All the components are there. So our null hypothesis is that the difference between the means is 0. Okay. And so we're running a two-tailed test here. We have on the right-hand side a T statistic of negative 3.73, 198 degrees of freedom. We know how we get the degrees of freedom, right? We have N1 minus 1 plus N2 minus 1. And you can see above, our observation numbers are 91. So it's 91 minus 1 and 109 minus 1. So I'm adding 90 and 108. All right. Notice here, what's missing? There are no p-values. So this brings me back to the olden days when we had to do things always using our T tables. Well, if I were to give you a question on a quiz and you did not have any p-values, and that could very well be the case, you would be forced to look at the T statistic versus the T critical. And I like to do this to my undergraduate economics majors because otherwise they just start memorizing how to tell from a p-value. And then you ask them what a p-value is, and they have absolutely no idea. So you've got to understand this. If you can understand this, you can do any test. You can do a z-test, a chi-squared test. There's other types of tests with other kinds of distributions, and they all work the same way. You look at the statistic versus the critical version from your distribution. All right, let's go on. So you should practice this one and make sure you can get the right results. So we want to ask ourselves, can we reject the null hypothesis at 95%? What about 99%? Well, again, to do that, you have to be able to, since you don't have p-values, go to this T distribution, but I have a degrees of freedom of 198. And you notice on this table, it stops at 29. That's because as numbers get large, these numbers get really close together. So you would just use for large degrees of freedom. So that's what I'm using. You're going to be where I've got that red box. So if we're running a two-tailed test at 0.05 level of significance, look what my critical T is, 1.960. If I want to run a 99% test, well, look at what our critical T is, all the way to the left, 2.575 it looks like, right? Well, we know with a critical T of 1.96 for 95% confidence, and for 99% confidence, we just found a critical T of 2.576. And keep in mind, we have our T statistic of negative 3.73. Remember, we take the absolute value of that. Do you agree that if you start by saying it's statistically significant difference between these two means at the 95% level, you shouldn't stop there because you might be able to say something stronger. So what about 99%? Well, at 99%, we still can reject the null. So what's my conclusion? We have a statistically significant difference in these means, and would I say it's significant at 95% and 99%? Would that be weird to say it? Yeah, that'd be kind of weird to say it. Why? Because if you have a significant result at 99% confidence, then clearly it would also be a result at 95% confidence. So you wouldn't say it's significant at 95, it's significant at 99, blah, blah, blah. That would make no sense. You just report the highest level. It is significant at 99% confidence, an alpha of 0.01. All right, you get the idea. So this is not hard. We're doing the same thing over and over again. So let's wrap it up, folks. We are using the t-test to test differences in means. Our hypothesis test is what we're conducting. You've got to think about the one versus two-tailed test because as I've shown you, it matters. There's a different hurdle for a one-tailed versus a two-tailed test. The one-tailed has a slightly lower hurdle than the two-tailed. So if you're going to tell me something is a one-tailed test, you better have a good reason for making it a one-tailed test. Once we decide and we've crafted our hypotheses, we need to use our t-statistic. Remember, where does that come from? It comes from our Excel output, or if you're using R or Stata or SAS or something like that, versus the t-critical. The t-critical comes from that table that is characterizing the t-distribution. Of course, you can also look at the p-values. You better understand what a p-value is. As I just said, if you're making a one-tailed test, make sure you explain or justify that assumption because it's an easier test to, I'm going to say pass. What I mean is reject the null, right? So craft your hypotheses accordingly, but do explain them. Be sure that you make accurate conclusions, that when you're doing hypothesis testing, that you state things correctly and accurately. Precision is going to be important. All right, so hopefully that is a good review for you and you feel like you understand this topic just a little bit better. Of course, if you have any questions at all, let me know. Otherwise, thanks for listening, guys, and I hope you have a fantastic day.